Okay, and the next doubt posed in the group is, if the potential energy of a body of mass m on the surface of Earth is taken as 0. Okay, surface of Earth is taken as 0. Okay, so which means I can't use the normal formula. That is usually the potential energy formula is minus gmm by r. Remember, this formula works and has been derived under the assumption that potential energy is 0 when r goes to infinity. That is, at infinity, potential energy is 0, and any distance less than that, it is less than 0. That's why the potential energy is negative. Okay, so again, potential energy 0 is my choice. Watch the class videos in work per energy and everything. I would have mentioned that potential energy 0 is our choice. Changing the 0 does not affect the actual calculations. Okay, and so it's my choice. So here they deliberately asked me to take potential energy to be 0 at the surface of Earth. Then it's potential energy at a height h above the surface of the Earth is. Okay, you see, you can take 0 anywhere you wish. Okay, but the concept, the general formulas will remain the same. What's the main idea of potential energy? Potential energy is defined because it helps us to calculate the work done. So work done by the external applied force will always be equal to, when it is doing work against a conservative force, gravity is conservative force, will be equal to change in potential energy. That's all. Work done by the work done by conservative force is negative change in potential energy, but here the work done by the external force. Okay, because potential energy is defined as work done by the external force to move it from one point to other point, like that. Okay, so this is potential energy final minus potential energy initial, and this is the work done. Okay, now what you need to know here, they are saying initially it's on the surface of the Earth, the object, and you have applied some force to move it to some height h. I don't know whether the height is small or large, so we're going to do it generally. Okay, so final is point B, initial is point A, and initially it will be at a distance of capital R from the center, and finally it will be at a distance of R plus h. Okay, and here the assumption is what is that? Potential energy at height. What is it? Surface of Earth is taken to be 0. So surface of Earth means at A. So at A, this is taken as 0. You understand that? That's the given condition. So if I take this to be equal to 0, what is the potential energy at final? That is point B, right? So which means it's just the work done. How do you find work done? Again, watch the class videos playlist. Since it's a the applied force, I'm going to apply a force in this direction. Maybe I'll use a different color to move the object up. Okay, we assume it's moving very slow. So the force that I apply will be equal to the force with which the Earth is pulling it. So net force is 0. So it's moving very, 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 very slow. Okay. So here the force that I'm going to apply must be equal to the force of gravity. But what is the force of gravity acting on the object? It is mg, which is m into g capital M by r square. Okay, so as you can capital M by small r square, because if I'm the surface of Earth, it is capital R. As I move up in between random any location, this will be, I'm taking some random location as R. So if I'm at some location R, the gravity will be gm by small r square. Okay, that's the force of gravity acting on us. And it's a variable. As you can see, as R changes, the force changes. So whenever you have a variable force work done, you can find by integrating. So it is force displacement cos theta. This is the potential energy at B. That's what I'm supposed to find. And the integration limit R changes from capital R to capital R plus H. I hope this is clear. Capital R to capital R plus H. And a cos theta, you see, I'm applying a force in the, let's say, upward direction, and the object is also moving up. This is the displacement. So force and displacement are in the same direction. Angle is 0, cos 0 is 1. So it is integral f dr. F is g capital M small m by r square into dr. This is what I want. Okay, so let's do the integration. So r into r to r plus h. So gmm will come out 1 by r square. When I integrate, I'll be getting minus 1 by r, limit r to r plus h. Okay, and this is what I need, potential energy at B. Upper limit minus lower limit. So this is gmm minus 1 by r plus h, minus of minus. So it will be plus 1 by r. And if I take an LCM here, this is gmm r into r plus h, which is minus r plus h. So this will be giving me RR cancels. I have gmmh by r into r plus h, and this is equal to the potential energy at point B. Okay, and see, it is positive. The reason it is positive, because we have taken potential energy to be 0 at the surface. So anything above the surface is positive potential energy, below the surface will be negative. And the normal formula we use is that you remember minus gm by r. Why is it minus? Because we take potential energy to be 0 at infinity. So you're below infinity, right? So it is negative. Okay, that's why always the potential energy was negative. But fine. So I hope you understand. You see, you can take 0 anywhere. You can always use this is the general definition. This will always work. Work done by the external force is change in potential energy. Work done by the conservative force will be negative change in potential energy. To get the better ideas about this, watch the class videos in the 11th playlist. Complete videos are available. And if you have any other doubts, you can post it in the Telegram channel. So keep practicing. All the best. Again.